Hello, everyone. In this video, we will talk about what operating system do and the interface of operating system. A computer system can be divided into 4 layers. The bottom layer, we have computer hardware, including CPU, main memory, input-output devices. Above the computer hardware, we have a software operating system. And then above the operating system, we have application programs, including the compilers, web browsers, and media players, word processors. And then above the application program, we have users. The hardware, computer hardware, can provide the basic computing resources, including CPU, main memory, input-output devices. An operating system is a very important software above the hardware. An operating system controls and coordinates the use of hardware resources among various applications. An operating system also provides users and applications with easy-to-use hardware resources. And application programs, these programs define how the system resources are used to solve a problem or to complete a task. The commonly used application programs are word processor, compilers, web browser, database systems, video games, media players, etc. And users can be people or the other application programs. Now, in this 4-layer computer system, what operating system do? In fact, there is no general accepted definition of what an operating system is. So an easier way to define an operating system is from what operating systems do than what they are. The operating system is the most fundamental software that runs on a computer. It performs 2 basic functions. First basic function, we see the operating system from a top-down view or from the user's view. From the user's view, the operating system provides programmers a set of clean, high-level, and abstract hardware resources. Now, we can see the operating system isolate users and programmers from the hardware and hide the complexity of hardware devices from users and programmers. Now, simply put, there is a great deal of complicated logic involved in communicating with hardware. Rather than forcing every application programmer to understand and replicate this complicated logic every time they access hardware, it makes sense to write a set of functions and place these functions in the operating system and allow users and the application programmers to call them. For example, if we want to read a file from a hard disk, if we don't have operating system, as a programmer, we need to check the index sector to get the address of this file. Here, the address means the track and the sector the file on. So we seek to the track number and seek to the sector number and read the content on that sector. Now, this is a very complicated. Now, the disk driver in operating system encapsulates this process. and it provides clean and easy interface. For example, the read system call. Now, as a programmer, we can just call the system call read and pass the file name to this system call or to this function, and then we can get the file content. So this is from the user's view. And from the bottom-up view or from the computer's view. So we know at the bottom level, we have the computer hardware. So from the computer's view, from the computer hardware's view, the operating system provides orderly and controlled allocation and management of hardware resources. So from the computer's view, the bottom-up view, operating system is a resource manager. It is a resource manager. A computer system has many resources that may be required to solve a problem or to complete a task. For example, the CPU time is a resource. The main memory space, the storage space, input, output devices, these are all hardware resources. Operating system manage and allocate these resources to the different program or to the different applications. Operating system decide how to allocate resources to which programs. So for example, when we run a program, we have an executable file main, and we run this program. So we need to load and run this program in the main memory. And the operating system will determine how long this program can use CPU time, or how long this program can run on the CPU, and how many memory space will be allocated to this program, and which address or where the program will be loaded in the main memory. Especially when multiple programs are running at the same time on a computer system, these multiple running programs, they may request non-shareable resources. So they may have conflict on these resources. Now the operating system need to allocate these resources to those programs in a way so that all programs can complete and the CPU utilization also very high. So all this resource allocation, resource sharing, and coordination, the scheduling of resources are transparent to users and application programmers, and the operating system will handle this resource management for us. Now, from the user's view, the operating system provide users and the application programmers with easy to use interfaces to access hardware resources, so that we can get the help on the programming execution, to use the input output devices to manipulate file systems, and to complete the communication between different programs to detect errors. From the computer's view, when the operating system works as a resource manager, the operating system help to manage processes, manage cache, manage memory, main memory, manage the secondary storage, input, output devices, and manage the file system, and complete the protection and the security service. Now the interfaces of operating system. The operating system have many different type of interfaces to users and application programmers. These interfaces can take several forms. Now, the most commonly used form is graphic user interface. Graphic user interface. Now, this interface is a Windows system. Now, we use a mouse to point, to drag, or to click, and to complete a task or to solve a problem. Now I'm using the graphic user interface in the Mac OS. Another option is a command line interface, or we call it command interpreter. It's known as shells in Linux and Unix. This means we need to use a keyboard to type in command in a specific format, and then ask the kernel to complete the a task or to solve a problem. So here the kernel is a program reside in the main memory at all times on a computer. Now in this course, kernel and operating system, these two concepts, they're interchangeable. Why we use a kernel? Why I introduce a kernel here? Because when we read some reading material or the reference book, you will see this concept a lot, kernel. But in this course, when I say the kernel, operating system, they're same thing, interchangeable. So for the interface for users, we have the graphic user interface and command line interface or shell. And for the application developers or the programmers, the operating system has two interfaces. One is a system calls, and another one is a standard C library routines. Now, from this figure, we can see the kernel. Inside the kernel, we have system calls. And then outside the kernel, the system call, we have shell or the command line interface. And then the library routines. Now, the shell and library routines, they all call the system calls to access kernel. And now let's take a look at the command line interface, system call, and the standard C library routines in detail. The command line interface or the command line interpreter, they also known as shells in the Linux and Unix. A shell is a program that acts as an interface between a user and the kernel. It allows a user to give command to the shell and receive response from the kernel. Now the shell or the command line interface or the command interpreter, they are not part of kernel. There are several different shells on Linux or the Unix. So we have the C shell, the BA shell or bash, A shell, K shell, etc. In the homework assignment shell programming, we will practice BA shell or the bash. The commonly used shell command, we have the ls, list the folder and the command in the current directory. mkdir, this is we create a new directory. cd change directory, rm remove, delete a file or directory, cp copy and move. Now the shell commands are documented in the section 1 of Linux manual. Now I will share the terminal. I will show you how to connect to the Linux machine in CSE Linux Lab. Now this is the terminal. Now I will connect to the Linux Lab. So first step, I use SSH to connect to the server. I add my Coyote ID and add gbh3-1.cse.csusb.edu. Enter your Coyote password. When you enter the password, nothing shows on the screen, but you just enter the correct password and press enter. When you see your Coyote ID at the host name, the server name, means you already connect to the server. And then next step, I will connect to the Linux machine. SSH GB359-2. GB359 is a CSE Linux lab at the third floor of GB building. There are many, I think 30 Linux machines in that lab. Now I will connect to the -2. So you can add any number between 0 and 10. I connect to 2, press enter. Now ls means list all the files for the directory under the current directory. Now cd CSE4600. Now I change directory. Here I have a folder named CSE4600. Now I change the directory to this folder. pwd, this is a shell command. Now this shows the current work directory. Now I'm under the home csusb.edu, my Coyote ID and the CSE4600. Now all the command I type here is a BA shell command. Now if I type the main -s1 intro, now type this command, we can open the introduction page of the shell command. Now this page, introduction to user command. The section 1 of the Linux menu describes user commands and tools. For example, the file manipulation tools, the shell, compiler, etc. Now to exit this page, press Q. Now I can use it. Now if I have some shell command, I want to know how to use this shell command. I type the main S1. Now I will type, let me see how to use the command ls. So ls, this command, this shell command, list directory content. Now the description lists information about the files. Now we can add the different options to this command. Now I add the -l. Let's see the -l. Use a long listing format. ls-l. Now, ls, I list all the files under this the current folder. Now I have the long format. I have the user account, the account information, and the timestamp for this file. This is a folder or this is a file. Okay, this is a shell command we can use on the Linux or the Unix. Now here we also can write the shell script file to complete a task or to solve a problem. In the assignment 1, we have a programming question. So you will write a shell script file. But I will record a video about the shell programming. Now the system calls in Linux or the Unix. System calls provide an interface to the kernel function or services. System calls are part of kernel. This is very important. System calls are part of kernel. And the system calls provide an interface to kernel services or the kernel functions. System calls in Linux and Unix are typically written in programming language C. Because the Linux and the Unix operating system, they are written in C. So the system calls provided by this Linux or Unix also written in C. The system call wrappers are documented in the section 2 of the Linux manual. Now the section 1 of the Linux manual, we have the user command, shell command. And the section 2, we have the system call, or we say the system call wrappers. Their definitions are also written in C. Now to check the introduction page of the section 2, we can type this command. The manual page of the Linux manual page, section 2, introduction. If we want to know how to use a system call, we type this command, manual page, section 2, the system call name. For example, the main section 2 read. This will show us how to use the read this system call. Okay, now I will show you this, the main dash S2. This means the section 2 of the manual page, introduction page. Now the section 2, this is the introduction to system calls. Section 2 of Linux manual describes the Linux system calls. A system call is an entry point into the Linux kernel. Usually, the system calls are not invoked directly. Instead, most system calls have corresponding C library wrapper functions, which perform the steps required. We will talk about the C library function later. But from the section 2, you can check all the system calls provided by the Linux or the Unix. Okay, now I exit this page. Now the main.s2. Now I want to know how to use this read system call. So I will check the section 2 of the manual page. Now the section 2, you can see this system call I want to see is read in the section 2. The read system call aim to read from a file descriptor. To call this system call, we need to include this header file. And this is the signature of this system call. We need to pass the 3 arguments to this system calls. And return value, etc. Okay, now I will go back to the lecture notes. The system calls are very useful. Even simple programs may make heavy use of system calls. Now we have this command cat main.cpp. Cat is a shell command. This command means print out this file to the standard output to the screen. If we add the strings in from this function, this strings command will print out all the system calls called by this program. So that means if we want to print out main.cpp to the screen, what system calls are called in this program, in this when the operating system executes this task. And now the CP means copy. We copy the source file to the destination file. Now we add the strings in front of this command, CP. So the strings command will show us what system calls are called during this during the CP command copy the source file to the destination file. Now I will show you this example. Now let me see what we have under my current directory. Okay, now I have the main.cpp. So main.cpp, we use this file in when we talk about the software compilation. Now the cat main.cpp. Cat main.cpp. This is a very simple CPP file. We have 3 local variables and z equal to x plus y. And I generate the assembly code for this file, g++ dash s main.cpp. Now I get the main.s. Now I print out the main.s assembly code to the screen. Now we have this assembly instructions. We already talked about this in last video, so I will skip this part. Now for the main head, now I want to show you what the cat command does here. Now cat is a shell command. Now we're open the page in the section 1. The cat concatenate files and print on the standard output. Standard output means a screen or the monitor. Now I quick exit this menu page. And now I tap the strings and cat main.cpp. Now I print out the main.cpp to the screen. Now I want to see what system calls are called during this process. Okay, now we can see here, this command, the output start from here. The first system call is a execve. And then next one is a break. And then the arc PRCTL and access openet state, openet and a state, openet state. Now we can see the at least 50 or the 60 system calls are called for this shell command to print out this file to the screen. And now we also have the read system call close, and exit. All these system calls are called. Now let me try one more. Stress cp main.cpp and test.cpp. The main.cpp is in our folder. Now I want to copy main.cpp to the destination file test.cpp. Now let's see. I think hundreds of system calls are called, yeah, from here. Now, this is a very simple shell command, cp, copy. And now it calls hundreds system calls. So that's why we see a simple program may make heavy use of system calls. Now let's go back to the lecture notes. Now this is example, the system call sequence to copy the source file to the destination file. Now we have the different types of system calls. We have the system calls for process control, for the files management, the device management, and information maintenance, communication, and protection. Next module, the module 2, when we talk about the processes, we will focus on this. How can we call the system calls to create a process, to remove a process, or to terminate a process? Okay, this is a system calls. And then we also have the API. The application programmers or the developers can access the API. API means the application programming interface. An API specifies a set of functions that are available to programmers. Now the developer, the application developers, programmers, they code according to a high-level application programming interface API, rather than directly call system calls. So there are several reasons for doing so. One benefit is program portability. An application programmer design a program using an API can expect her or his program to compile and run on any computer system that support the same API. Furthermore, actual system calls can often be more detailed and difficult to work with than the API available to an application programmer. So now as a programmer, we often call the API instead of call the system calls directly. But the API functions call actual system calls in the kernel to access the kernel services and to access the kernel functions. Now a programmer access an API via a library. So such as the glabc in Linux. glabc wraps the system calls. Many system calls have functions of the same names in the standard C library glabc. Now the section 3 of the Linux manual describes all the library functions, excluding the library functions described in section 2. In section 2, we have system call wrappers. So the section 3 describes all the library functions except or the excluding the system call wrappers. Now, if we want to know the standard C library function, we can check the introduction page of section 3. If we want to know how to use a function defined in the standard C library, we can check the main manual page, section 3, and add the function name. Now I will show you this example. Now, the manual page -S3 introduction page of section 3. Now this introduction to library functions. The section 3 of Linux manual describes all the library functions, excluding the system call wrappers described in section 2. So we know the section 2, the system call wrappers implement system calls. Now many of the functions described in section 3 are part of standard C library, labc. Nowadays, we use a glabc. Okay, now section 3, read. Now we have the read system call. So if we type the -S2, we can see how to call the read system call. And now in the section 3, in the standard C library, we also have the read function. Now I checked how to use or how to call the read function in defined in the standard C library. I will add the -S3. Now read 3, this means this read is in the standard C library. Now the read from a file. Now how to use this function? We need to include this header file, and this is a function signatures. We need to pass 3 arguments to this function and a return type. So we have the description of this function and also the return value errors of this function. Now this image shows the standard C library function. Now here we have the standard, we have a function printf. This is a function defined in the standard C library. This means that we print out this string to the screen, to the standard output. And this function is defined in the standard C library. And this function called the write system call defined in the kernel. So we see all the standard C library function will call the system call to access the kernel functions or the kernel services. Okay, this video will stop here.